Chemical equilibrium is an extremely important concept for the MCAT to test you on in a variety of different topics. My name is Alyssa, and it's the goal of this video to help you understand the finer points of chemical equilibrium so that you can answer questions with confidence. We'll start off by looking into what dynamic equilibrium is, and then move on to discuss the law of mass action. Then, we'll investigate the reaction quotient and see how it relates to equilibrium, and finish off by revisiting the law of mass action to discuss some of its more important properties. After watching this video, you will be comfortable defining equilibrium in detail and explaining the difference between the equilibrium constant and the reaction quotient. You will be able to use this information to help you answer questions like this one that you could see on the MCAT. First, we will explore dynamic equilibria. A lot of the time in chemistry, we like to assume that reactions are irreversible, which means that reactants form products, but the products cannot revert back to the reactants. With equilibrium, we must realize that most reactions are reversible. Reactants can form products, and products can form reactants. These reactions usually do not go to completion because some of the products will always be reacting to form reactants again. Therefore, there is a certain point at which the concentration of the product will not change, regardless of the fact that reactant still remains in solution. Let's look at this on a concentration versus time graph using the simple reaction where A reacts to form B, but B can also react to form A again. Over time, the concentration of A in solution decreases and the concentration of B increases. Eventually, the concentration of products and reactants will level off, but this doesn't mean that the reaction has stopped. It only means that there is no change in the concentration of these species. What does this mean? Well, it means that the rate of the forward reaction, A to B, is the same as the rate of the reverse reaction, B to A. If A goes to B at the same rate as B goes to A, the concentration of these species cannot possibly change because they are forming and reacting at the same rate. Entropy is a measure of energy distribution throughout a chemical system, and at equilibrium, entropy is at a maximum and Gibbs free energy is at a minimum, which we all know is a favorable outcome. Therefore, why wouldn't the chemical system want to remain at that point? Now let's investigate the law of mass action. Let's assume that the following reaction has reached equilibrium, so the concentration of products and reactants is not changing, and that the temperature of the system remains constant. The law of mass action states that if these scenarios occur, the equilibrium constant of that given reaction is equal to the concentrations of the products divided by the concentrations of the reactants, with each concentration term raised to the stoichiometric coefficient for each species. This ratio is of course constant when the concentrations of the compounds in the reaction are not changing. It is also directly related to the rates of both the forward and the reverse reactions. Let's simplify the reaction so that we can understand what this means. Take this one-step reversible reaction where two molecules of A react to form a molecule of B and a molecule of C. Remember, this reaction occurs in both directions. Using the rate law, we see that the rate of the forward reaction is the forward rate constant Kf multiplied by the concentration of the reactants. And the reverse rate is found by multiplying the reverse rate constant Kr by the concentration of the products. We just said that at equilibrium, the rate of the forward and reverse reactions are the same, so we can set these two rate equations equal to one another. Then, we rearrange the equation so that we can see something rather interesting. Since Kf and Kr are constants, their quotient will be a constant as well. It is this value that is called the equilibrium constant, and this is the process through which we obtain the equilibrium expression above. The subscript EQ means that the reaction is occurring in a dilute solution. If we were to look at a reaction of gases in equilibrium, the equilibrium constant would be denoted Kp, because we are looking at the products and reactants in terms of pressure. The subscript can also be a C, which just tells you that we are focusing on the concentration of the components in the reaction. What about the more complex reactions? Take this reaction, which we will assume is a three-step reaction. This time, we can find the equilibrium constant by multiplying the equilibrium constants of all three steps. Remember that the equilibrium constants are found by taking the ratio of the forward reaction rate to that of the reverse reaction rate. we can see that the equilibrium constant for this three-step reaction is still found by the ratio of concentration of products to the concentration of reactants. When studying and doing your practice problems on this topic, make sure that you do not confuse the two different K's. Anytime you see a capital K, make sure you think equilibrium constants and therefore equilibrium expressions. If you see a lowercase k in an equation, you should think of rate constants and rate laws for reactions. We just looked at how to calculate the equilibrium constant, but how do we know if a reaction is at equilibrium or not? Well, we use something called the reaction quotient, Q, which is used to determine how close the reaction is to equilibrium. This value is calculated using the equation below. It looks familiar, doesn't it? It's almost identical to the equilibrium expression we defined earlier. However, this reaction provides us with different information from the equilibrium expression. But how? In the equilibrium expression, the reaction is of course at equilibrium, and so the concentrations of the reactants and products are constant. With the reaction quotient, the concentrations are changing since the reaction is not yet at equilibrium. Therefore, we calculate the reaction quotient at a moment in time, and use it to compare to the equilibrium constant. There are three different outcomes for this calculation. The first is when the reaction quotient is less than the equilibrium constant. This means that the reaction rates are not equal and that the forward reaction has not yet reached equilibrium. If the reaction is proceeding in a forward direction, the change in Gibbs free energy must be less than 0 and the reaction is flowing favorably towards the products. If Q is smaller than the equilibrium constant, there is a higher concentration of reactants and a lower concentration of products at this time than when the reaction is at equilibrium. What about if the reaction quotient is equal to the equilibrium constant? Well, this means that the reaction is in dynamic equilibrium. There is no change in Gibbs free energy because the reaction has no net movement in either a forward or a reverse direction, and the concentrations of the reactants and the products are not changing. The last outcome is that the reaction quotient is greater than the equilibrium constant. This means that the forward reaction has exceeded equilibrium. The change in Gibbs free energy is positive, and the reaction is proceeding in the reverse direction towards the reactants. At this point in the reaction, there is a larger concentration of products and a lower concentration of reactants than when the reaction is at equilibrium. What does this all mean in terms of a reaction, though? Think about this chemical equation, the dissociation of an acid in water. Here, we are adding more and more acid to the water, and the molecules are dissociating into ions. At this early stage of the reaction quotient is less than the equilibrium constant, and there are more reactants present than when the reaction is at equilibrium. Therefore, we know that the change in Gibbs free energy is negative, and the reaction is moving towards the formation of more products, in this case dissociated ions. We let the reaction continue forward. Now the reaction quotient is equal to the equilibrium constant. Delta G is 0, and the reaction is at equilibrium. Say we then add even more acid to the solution. Now the reaction quotient is greater than the equilibrium constant, and the change in Gibbs free energy is positive. The reaction then proceeds in the reverse direction and forms reactants. When the reaction reaches equilibrium again, the concentrations are different from before since we have added more acid to the solution, but the forward and the reverse reaction rates are still equal, and products are forming at the same rate as they are breaking down to form reactants. We'll finish off by investigating some important properties of the law of mass action. The first is that pure solids and liquids do not appear in the equilibrium expression. This has to do with the fact that for pure solids and liquids, the activity of these compounds is 1. Within the scope of the MCAT, there is really no difference between activity and concentration, and so these compounds are left out of the equation, since we would really only be multiplying or dividing by 1, a redundant operation. The second property is that the equilibrium constant is temperature dependent. Depending on the reaction, adding heat will form more products. Therefore, at this elevated temperature, when the reaction reaches equilibrium, the ratio of the concentration of products to the concentration of reactants has changed, or, more simply, the equilibrium constant has changed. A very important property is that if K equilibrium is large, the equilibrium position is more towards the products, and their concentration is higher than the reactants. This is what we chemists want in a chemical reaction. Looking at the equilibrium expression above, when K equilibrium is large, the top number is large and the bottom number is small. This represents a reaction with a lot more product than reactant. Lastly, we can determine the equilibrium constant for the reverse reaction, in this case, compounds C and D forming compounds A and B, by taking the inverse of the equilibrium constant for the forward reaction. If the forward reaction has a large equilibrium constant and favors the formation of products C and D, the reverse reaction will still favor the formation of C and D, though in this case, C and D are the reactants, and therefore the equilibrium constant will be small. Equilibrium is an important topic for the MCAT to test you on, so let's try some practice questions to test your understanding of this topic. This question is asking you to think about the equilibrium expression for this given reaction. The answer is B. Remember that the equilibrium expression is the ratio of the concentration of the products to the concentration of the reactants. That gives us the following expression, including the coefficients of the reaction as exponents in the expression. In this equation, hydrochloric gas and oxygen gas are the products, and so would be at the top of this expression, whereas steam and chlorine gas are the reactants, and so would be at the bottom of the expression. That eliminates answer choices A and C, and leaves us with answer choices B and D. We know that the answer choice D is incorrect because it doesn't include the stoichiometric coefficients from the equation as exponents in the equilibrium expression. This second question is asking you to think about how you can determine whether a reaction is reaching or has exceeded equilibrium. The answer is D. The reaction is occurring in the reverse direction and has a positive delta G value. To solve this problem, we need to find the reaction quotient and compare it to the given equilibrium constant. Remember that this is the ratio of the concentration of the products to the reactants, and these values are given in the question, so we can calculate Q to be 5 times 10 to the minus 3. This value is larger than that for the equilibrium constant that was given in the question. When Q is larger than K equilibrium, the reaction has more products than reactants when compared to equilibrium, and so the reaction must move in a reverse direction to reach equilibrium, resulting in a positive value for the change in Gibbs free energy. Great job if you got those questions correct. In this video, we learned the important concepts within equilibrium. We saw that in dynamic equilibria, the reaction is still occurring, even though there is no change in the concentration of the reactants or the products. This means that the rate of the forward reaction and the rate of the reverse reaction must be the same. We defined the law of mass action for reactions and saw that the ratio of the concentration of the products to the concentration of the reactants at equilibrium was equal to the equilibrium constant. We also looked into the important properties of this law. We do not include pure liquids or solids in the expression. The equilibrium constant is temperature dependent. If K equilibrium is large, the reaction will form a high concentration of the products, and if we need to know the equilibrium constant for the reverse reaction, we just need to find the inverse of the equilibrium constant for the forward reaction. Lastly, we learned about the reaction quotient, which tells us whether a reaction is reaching equilibrium or has surpassed it. When Q is less than K equilibrium, there are more reactants than products at this point of the reaction than at equilibrium, and the reaction is moving spontaneously towards the formation of products. If Q equals K equilibrium, the reaction is said to be in dynamic equilibrium. And finally, if Q is larger than K equilibrium, there are more products than reactants at this point of the reaction than at equilibrium, and this time the reaction is proceeding towards the formation of reactants in order to reach equilibrium. Thank you for watching this video, and good luck studying for your MCAT.